In problem number 8, we need to find the tangent plane to the paraboloid given by the equation z equals to 2x squared plus y squared at the point with the x coordinate equal to 1 and y coordinate equal to also 1. And the question in the problem is, what is the z-intercept of this tangent plane? Let's begin by calculating the z-coordinate of the point on this paraboloid, which has the given x and y coordinates. This is fairly simple. All we need to do to find the z-coordinate is to plug in x equals to 1 and y equals to 1 into the equation for this function. And so then the z value will equal 2 times 1 squared plus 1 squared, and that is equal to 3. So the point P on the graph of this function, where we will be drawing the tangent line, is the point with coordinates 1, 1, 3. The tangent plane will be tangent to the graph of the function at this point P. It might help us to get a better idea how it looks. So here is the graph of this function. So sort of looks like a cup. It's called a paraboloid because if you look at the grid lines on the surface, these grid lines are parabolas. And what these grid lines are, they are cross sections of the graph by planes perpendicular to the x-axis and the y-axis. Now let's and also I want to point out here the point P is marked as well. And so what we are looking for is the tangent plane that will touch the paraboloid at this point P. And now I'm going to bring this tangent plane into the picture. So here it is. Now let me rotate the view so we can get a better idea how it looks. In this case, you can see from this graph that the tangent plane, shown in green, touches the paraboloid at a single point, namely point P, and nowhere else. That's not always the case, but for surface like this one, it is the case. And so what we're looking for is the equation of this green plane, and that would allow us to calculate the z-intercept. Now if I'm positioning this graph correctly, we will see our answer. Here it is. You can actually see here on this graph that the z-intercept of the plane equals to -3. Well, let's see if we can obtain this result by a calculation. So let's recall the general formula for the tangent plane to the graph of a function z equals to f of xy at a point with coordinates a for x, b for y, and then c for z. The equation of the tangent plane is the following, and really these formulas are very similar to the equation of the tangent line to the graph of a function of a single variable at some point. So the equation of the tangent plane is z minus the z coordinate of the point P, so z minus c equals the value of the partial derivative of f with respect to x evaluated at the point AB. So this will be a number, kind of like a slope in the x direction, multiplied by x minus the x coordinate of the point, so x times x minus a, and then plus partial derivative of f with respect to y, again evaluated at our point AB, and then multiplied by y minus b. And that is the equation of our tangent plane. It is useful and correct to think about these partial derivatives df dx and df dy at the point AB as the slopes of our plane in two directions, one in the direction of x-axis and the other in the direction of the y-axis. And so really this formula is very similar to the equation of the tangent line. Has exact same structure, except that on the right hand side now it has two terms, and you would expect that it would have to contain several terms because now our function depends not only on x but also on y. So to write down the equation of the tangent plane, we need to know the values of partial derivatives of our function. The values of a, b, and c are already known to us. Okay, so z equals to 2x squared plus y squared, right? I think, yes. And so let's go ahead and calculate our partial derivatives. So the partial derivative of z with respect to x is going to be 4x, and we will plug in x equals to 1 to evaluate our partial derivative at our point, 1, 1, and that's going to be 4. Similarly, the partial derivative of z with respect to y will be 2y, and if we plug in y equals to 1, that's going to be 2. So dz dy evaluated at the point 1, 1 is going to be 2. Now all that's left for us is to plug in these numbers into the equation of the tangent plane in general form that I just wrote right here into this equation. We have all the pieces now. Maybe I'll start writing here. Yeah, so c value is 3 as we found earlier, so we're going to get z minus 3 equals partial derivative with respect to x equals to 4. So 4 times x minus 1. Partial derivative with respect to y is equal to 2 and times y minus 1. Very good. So now let's simplify this equation. I'm going to move the negative 3 term to the right hand side, and also will distribute 4 to the two terms in parentheses here. So 4x minus 4, and distribute 2 to the two terms in parentheses, and we'll get z equals 4x minus 4 plus 2y minus 2 plus 3. Z equals 4x plus 2y. And then for the constant terms, negative 4, negative 2, negative 6, plus 3, negative 3. Okay, so this is the equation of the tangent plane. Now to find the z-intercept of this plane, again, very similar to how we would find the y-intercept of the tangent line, we need to plug in x equals to 0 and y equals to 0, right? Because we're looking for the point on the z-axis where the plane meets the z-axis. But all points on the z-axis have x a coordinate equal to 0 and the y coordinate equal to 0. And so if we substitute x equals to 0 and y equals to 0, we will get the following z value: 4 times 0 plus 2 times 0 minus 3, which is negative 3. And that is exactly what we saw on the graph. The tangent plane intersected the z-axis at the point negative 3.